Has to.
Yeah, a lot of people actually did better, but we'll talk about that afterwards. Okay, so let's begin.
Bless you.
So looking at the final, so let's talk about the final. Let's start there. Looking at the final, it's no surprise really, honestly, but there's still some things that I have to talk about to make sure that we're solid on them. We'll talk about that. Maybe we'll talk a little bit about that cool thing about eigenvalues and eigenvectors, and I can use the same example we did last time. And so it's not a final review, it's just info on the final. Do you guys remember when your final is?
24th?
May 24th.
May 24th. So make sure you know that in the time. I'll give you the room number later. So it's May 24th. The format is the 11 problems are given. And you'll ultimately do 10 problems. Right? So it's a 2-hour and 15-minute exam, so that kind of, you can plan now, you know what time limit you should be able to finish each problem in. So it's going to be roughly, you have to do 10 problems in 2 hours and 15 minutes. Yeah, 9 is more typical, but 10, it depends on the how good you are.
Wait, how many questions were the test? Like 4?
So there are 2 parts. There's a part 1, and this has 7 problems. And this is compulsory. You have to do all the problems in that section, and then there's a part 2 where you have a choice. So you'd be given 4 problems, complete any 3. And no, you won't get extra credit for doing more than 3.
Aww.
If you do more than 3, I'll grade the best 3, but that's the only mercy you'll get at this point.
Oh, you grade
all the extra credit on exams, you should have gotten it before this point. You had 4 tests to get all the extra credit you needed.
What's the next extra credit?
So that's the format. In terms of how it looks, it's actually written by the same guy who wrote the last 2 finals. You'll notice that when I give you reviews for exams, I didn't actually put all the final exams on that review, and that was actually intentional. So if you look at, if those of you who went ahead and did it anyway, studying for the final will be less effective for you. You're going to have to work a little bit harder. But for those of you who do the bare minimum and like, oh, I'm not even going to look at Jhevon didn't assign these problems, you guys get to benefit from this. The rest of you, you've seen the problems before, and so redoing them is probably not going to mean as much. But if you look at the spring 16 and spring 17 finals, I never put those on any review, and it's written, the same guy who wrote this finals is the guy who wrote those. So in preparing for the finals, I would recommend that you find the time to actually sit down and do these 2 finals in their entirety in one sitting. You put a clock on yourself, 2 hours and 15 minutes, you do this and you do that, and you do that before May 24th. That would be the best. That would be the best kind of review. So what I would probably do, since we have 2 finals to work with, I'd probably study a little bit to the point where you kind of think you'll do okay, do one of them, and then assess yourself. You can ask me if you have any questions, or go to tutoring or whatever. And if you actually didn't do well on that by your self-assessment, you study deeper, and then you retest yourself on this. So don't take them one right after the other. I would do one, assess where you are, see where your weak points are, use one kind of like a diagnostic, and then try to fill in your gaps, and then hit the second one. So that's how I would prepare. Other than that, I probably go over some of the old finals again, especially with topics that you haven't done for a long time, so you're not going to like remember the solution, right? Because there's the danger of because you did it before, you're doing it again, you'll remember the solution and you think, oh yeah, I understand this, but you're really just memorizing it, didn't really understand. So you don't want that to happen. So for those of you who already did this, so you'll probably remember some of the problems, you'll have to figure out how to find yourself new problems to do. So if you didn't, the solutions aren't online, but hopefully at this point you'll be able to check yourself. So that's kind of where I would go. That being said, there are some kind of problems that even appeared on these that we have to talk about because they're kind of a little bit nuanced compared to what we've done before. Case in point, if you look at the web work problem, there's a problem that was in your web work homework, 3.8, problem 4.
3.8 or 13.8?
13.8, problem 4, which I have here. A problem like that came up on these two finals, and there's a problem like that on the final you will be taking on the 24th. And I'm pretty sure it's in the compulsory section, so this is kind of something you have to pay attention to. It's like, damn, I have to pay attention. I was about to zone out, but okay. Okay, so the problem was, it asked us to compute a line integral. So we had to find f dot dr. C is a circle, radius 3, in the plane x plus y plus z equals 4. This is slightly harder than one you might see on the final. So if you can get this, because the numbers here are kind of ugly, but the numbers are nicer on the final. Okay. It's centered at radius 3 in that plane, center 4, 4, minus 4. Clockwise orientation. When viewed from the origin. And finally, they have to tell you what your f is. Your f is 4y minus 2x. 4 times y minus x. So yeah, that's it. F dot dr sees that circle in that plane, centered there, clockwise orientation, when viewed from the origin, f is this, compute that line integral. Okay. So can someone tell me what's the obvious problem here? Like, what makes this difficult?
It's not centered at the or it's not centered at whatever origin, or there's no 0 in the center for one of the directions.
That doesn't make it difficult in general.
The circle's kind of
I mean, we have
tilted.
to parameterize the circle, and parameterizing the circle with an arbitrary center is not an issue in general.
Circle's kind of like tilted.
The circle is tilted. The circle is not something that is it's not parallel to the xy plane. It is in the plane. It's a plane in this plane, right? There's a circle in this plane, right? Which means if you project it to the xy plane, it's no longer a circle. It's going to be something else. It's going to be like elliptical. It's going to be like a weird shape. And something like that will be held to parameterize. So doing this directly and parameterizing would not be what you want to do. The idea here is we're going to use Stokes' theorem to compute this. So you want to notice the projection in any of the coordinate planes is not a circle, right? It's a circle in this slanted plane, right? But parameterizing it once we project it onto one of the coordinate planes, it's not a circle anymore. It's now something a lot more complicated. So the idea here use Stokes' theorem and stay out of the coordinate planes. In other words, do not project anything. You will be working in the surface S. So Stokes' theorem tells us what? F dot dr is equal to
A double integral.
double integral of curl F dot ds. Yes. Now what was that?
What?
How would we compute this? What does it mean to compute this guy?
Del cross F.
That's for this guy, the curl. I mean, talk about the entire surface integral. How would you compute it? What is the?
We need to get a normal vector.
You need to get the normal, and what do you actually compute at the end of the day to compute this?
The area of the projection?
The,
You dot the curl with the normal.
You dot the curl with the normal vector, which hopefully by now you know how to find the normal vector pretty easily. And what we've always done in class was I always put here D and dA, right? But it turns out that was the formula you get after projecting, right? dA is that guy you have from Calc 3, which represents dx dy, or dy dx, or dx dz, etc., right? It means projection in the coordinate plane. You're integrating over an area of projection in one of the coordinate planes. But there was an intermediate step you might have recalled, right? Where it was in the surface S, meaning we didn't project to the coordinate planes, was curl F dot n ds. And in particular, our n in that step was what?
Unit.
It was a unit vector. The idea was, because we know that, so this guy is actually a unit vector, which means he looks something like some vector over its magnitude. And it turns out that ds was actually equal to the magnitude dA. And so what happens was, when you start to swap these in, you cancel the magnitude, right, to put the dA in. But that's when you do a projection. Which means if you don't do a projection and you stay in your surface S, the normal vector you're using has to be the unit normal. Which means you're going to do what we did to find the normal vector, and then you're going to divide by its magnitude. Right? Now as long as you're in the surface S, which in this case the surface is the plane, now it's just a circle of radius 3. And once we stay in S, we know how to deal with circles. If we project to the dA interpretation, it's no longer a circle, and that's hard. So we're going to stay here just before projecting. And you'll see how the problem turns out now. So here's the idea. This is 4y minus 2x, 4y minus x. So the first thing we're going to do is we're going to find the curl. We're going to use Stokes. We're going to use the fact that this guy is equal to the double integral of curl f dot n ds, where this is a unit normal. And let's just find the pieces. Curl f would be I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, 4y. Minus 2x, 4y minus 4x. So this would give us 4 minus 0. This would give us minus 4 minus 0, but you change that, so that's plus 4. And this will give us minus 2, minus 4. Right, so you'll get that. We also know that our normal vector here, which we're taking to be the unit normal, is just the normal from the plane. And the plane was x plus y plus z equals 4, right? So the normal vector is 1, 1, 1, but we divide by its magnitude. So we're using the unit normal here. And so basically what that means is f dot dr, double integral over s of curl f dot n ds. Don't switch to dA, stay in ds, where my curl is now going to be 4, 4, minus 6. My n is going to be 1, 1, 1 over radical 3 ds. So that's going to become what? That's going to be 1 over radical 3 times 4 plus 4 minus 6, right? That's 8 minus 6, so that's 2. Of the double integral of s ds. And what's that?
Area of a circle.
The area of the projection in the surface S, which is just a circle. So it's pi times r. What was r? 3? Squared. That was it.
I think I accidentally did this the right way.
Yeah. So the trick was here to realize that when you have an object in a different surface, sometimes projecting it into the xy plane makes things harder. The surface is harder to get a hold on.
Professor,
Yes.
so when you put the n, don't you have to put n dA because,
No,
no?
that's what I'm explaining. When you go to dA, you're going to a projection. That's when you're
okay.
using a projection to evaluate the integral. Here I don't want to project. I want to stay in the
DS.
S universe. I don't want to go to the xy plane.
Okay.
I want to stay in the S plane.
Okay.
And staying in the S plane means I don't go here, which means I don't kill the magnitude, which means I use the unit normal in the calculation. And now I'm integrating with respect to the surface S.
Okay.
And so the double integral of 1 ds is just the area of S. Yeah?
Why is your vector pointing upwards?
Oh, did they say clockwise? We have to check the orientation, making sure.
Yes.
Clockwise.
So the plane was, it looked like this, right? And the center was what?
Yes, no.
4, 4, negative 4.
So 4, 4, negative 4. So the center, the circle is like down here somewhere. But we're looking from the origin. And when we're looking from that way, it's counterclockwise. So if we're looking from this way, it's
Hey, what are we? Clockwise from the origin?
Clockwise from the
Clockwise from the origin.
clockwise from the origin, right?
Yeah, so it would be pointing
So it's going here when I'm looking from the origin. So what does the right-hand rule say? It would be pointing up. It would, the z component should be positive.
Yeah.
So that's the right one. Yeah. You'd have to apply the right-hand rule. Yeah, so if I'm looking from here to there and it's going clockwise, that's how my right hand will be pointing. And since the plane is slanting this way, that means it will be pointing up. Yeah.
Will it always nicely cancel to just be the area of the shape?
Well, a problem like this, yeah.
Professor, so what areas would...
In 392, I mean, in actuality, probably not. But in 392, they're going to give you something where it nicely, everything is like a constant and it nicely cancels and you can just use your area formula.
So the area formulas we're using are just the shapes we've been doing, cones, spheres, etc.?
Yeah, it's area, so it has to be like a 2D figure. So area of a circle or area of a rectangle or something silly. Something that's silly in the S plane, but when you project it in the XY plane, it's complicated. So, and the trick is to just stay in the S plane. Do not go here. So that was first thing I wanted to talk about. But as this kind of suggests that you really want to pay attention to your definitions, and I feel like that's kind of a theme in this final, like you really have to pay attention to what. It's very computational, that's not, I'm not saying it's not, you won't have to like explain anything, but you need to know terms. So for example, you guys remember what rank is? I told you what rank was. It wasn't a kind of measured.
It was the number of pivots, right?
Number of pivots, right. So you put it in row echelon form or reduced row echelon form, count the number of pivots, and there are a lot of consequences to what this is in comparison to the number of columns there are, but you're not going to be asked about that. But you should be able to identify things that they can ask you about a matrix, like what's its rank, or what does this mean? Things like, do you know how to prove that F is conservative?
Partial.
Take its curl.
Partial.
It's curl if it's three-dimensional,
Oh.
right? So if your F is a three-dimensional vector field, then
Curl is 0.
and if components, of course this is kind of always going to be the case, but if the components have continuous partial derivatives on the region, blah blah blah. Then you know that F is conservative if the curl is the zero vector. What if it's a two-dimensional thing? Partial of what? What?
Qx minus qy.
Yes, minus zero.
Partial of p with respect to y must equal to the partial of q with respect to x. Right, so you have to check that. So there are two slightly different things. So based on 2D or 3D, you might have to do one or the other. You could also just find a potential function, but unless you're going to use it afterwards, I don't think it's worth wasting the time. So you can just do one of these two checks. You will have to apply the fundamental theorem of Lagrange-Grill at some point, so you should know how to find a potential function anyway. But if all the question says is just, is this conservative, yes or no, then doing one of these two checks for the two-dimensional, three-dimensional case respectively is fine. Another thing that stands out in this final is that he does talk about the physical interpretations a lot. So I told you about most of them, just there's one I didn't tell you about that I think you probably have to know. So we saw what this guy meant in the physical sense, right? If I interpreted F as a force, what was that?
Work.
Work. Right, it's the work done by the force field to move a particle along curve C. Okay, so that we could interpret as work. We had an interpretation for this guy, which was flux. And this is just the amount of stuff passing through the surface. Per unit area or volume per unit area of the surface. Okay, so that can be even a lot more general. So basically whatever interpretation you put on your F, you're counting how much of that is passing through a surface per unit time. Now, one interpretation that I didn't really do is back to the line integral with respect to arc length. The d lowercase integral. Now we spoke about the geometrical interpretation of this. It was the area of that fence and blah, 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 blah. But it also has a physical interpretation. It turns out that if we interpret F as the linear density at a point, then this is actually equal to almost. It's actually equal to the mass. Of the infinitesimal wire along C. So you'll find that very analogous to back in Calc 3 when you're looking at mass and center of mass. This is the guy that means that in higher dimensions. And so if you wanted to find, for example, the center of mass, this will be the coordinate x bar comma y bar, not vector bar, where x bar is 1 over m times x times our function, yes, and the y bar is 1 over m of y times our function. And this is n for mass. So for problem mass, you define the mass of a wire along this curve between this point and this point. This is your integral. Under the interpretation that f is measuring the density at a given point. So again, we know how to compute this. That's not anything new, but you need to understand an interpretation of it. So when a question asks you to do this, you know, oh, that's what it's talking about. So if you're asked about to find mass, you're actually using the line integral with respect to arc length. What else? I think that's pretty much it. Otherwise, it's a pretty normal final, and going through spring 16 and 17 would be pretty good practice. So not much more to say in that regard. I do want to, as we were talking about before, show you something cool about eigenvalues and eigenvectors. We did an example in class where we found the eigenvalues and eigenvectors of the matrix minus 5, 2, 2, minus 2. Was that it? What were the eigenvalues? I think one was minus 6 and minus 1. And their eigenvectors were minus 2, 1,
1, 2.
1, 2.
Yeah.
And we saw one application of that. We could actually use it to solve a system of linear differential equations, a 2x2 system of linear differential equations. Here's something else that's interesting. There's a theorem out there that says, suppose A n by n has n linearly independent. I mean, those of you who are taking differential equations know what this means, but the rest of you, it doesn't matter. Don't worry about it. Okay, linearly independent eigenvectors. Then A is called, then A is what we call diagonalizable. i.e., A can be written in the form where P is invertible meaning you can find an inverse, its determinant is non-zero, and D is a diagonal matrix. And in fact, we know exactly what these guys would look like. The matrix P will take this form. You take all the eigenvectors and you line them up in columns and put them in the matrix. So this is lambda 1 vector, first column, lambda 2 vector, second column, dot, dot, dot. You line up all these eigenvectors in columns, turn them into a matrix, that will be your matrix P. And it turns out that your diagonal will be on the main diagonal, will be the corresponding eigenvalues. So lambda 1 will be in the first row, corresponding to the first eigenvector. Lambda 2 will be in the second row, corresponding to the second eigenvector. And so on, all the way down to lambda n. These guys are all linearly independent, is equivalent to saying none of these guys will be 0. So you have a bunch of non-zero numbers along the diagonal and zeros everywhere else. And it turns out if a matrix has n eigenvectors that are linearly independent, you will be able to write it in this form, where the matrices are these matrices. In other words, this matrix I could actually write as -2, 1, 1, 2 times -6, -1, 0, 0. Times -2, 1, 1, 2 inverse. Okay, that's cool, but why would we want to do that? What's the point? Well, there are several points. Here's why an engineer would find this useful. Let's suppose A can be written in this form. Now let's look at the fact that if we want to multiply A by itself, not n, let's use the mother, because n is the number of rows here. Let's say we want to take A to the kth power. K is some arbitrary positive integer. What that means now is that we're pretty much going to be multiplying this by itself k times. Notice anything?
P and P inverse.
P's and the P inverses end up being right beside each other. Literally all the interior P's will cancel out. And ultimately this will be P times D to the K, P inverse. In other words, if A is a matrix that has n linearly independent eigenvectors, I can take its power by doing a product of 3 matrices. And it doesn't matter what power it is, it could be 1,000th power, it's still, I only have to multiply 3 matrices, not 1,000 of them. And in fact, before you're like, well, I still have to find D to the K, remember, D is a diagonal matrix. How do you multiply diagonal matrices by themselves? You just raise the components to the power, right? D to the K is really just this to the K, that to the K, that to the K, that to the K. So I can compute a lot of things. So if I wanted to, for example, find A to the 100th power, I'm not going to sit there and multiply A by itself 100 times. That is just going to be this times 6 to the 100th times this. Multiply those 3, I've just raised that matrix to the 100th power. It's going to be huge, I mean 6 to the 100th. It's huge, but yeah, in principle, that's how we would do it. So it can greatly simplify computation. Why a math person would like this theorem is that it turns out that the properties of the diagonal matrix, there are many properties that it shares in common with the original matrix. They'll have the same rank. They'll have the same eigenspace. They'll have the same trace. You might notice that -5 plus -2 is the same as -6 plus -1. There are a lot of properties that when you go from the land of matrices to the land of what linear algebra is really about, which is the study of linear transformations on vector spaces, all these properties of matrices have an interpretation in the functional space. And so knowing about the trace can mean something. And knowing about all these things can mean something. What you can, essentially what this gives you is it's the power to study some matrix by studying some equivalent diagonal matrix, where I know all the things with this diagonal matrix, they translate very easily back to the original matrix. So I can study a very complicated function by looking at a much simpler function. And studying the functions can tell you a lot of information. So, but computationally speaking, you have this nice property falling out. Yeah, so it turns out if an n by n matrix has n eigenvectors and they're all linearly independent, meaning you can't write any as a linear combination of the others, then this thing actually falls into your lap. You can diagonalize a matrix, write it in terms of some diagonal matrix, and you can study the original matrix by studying that matrix. And you can do a lot of computations on the original matrix by doing computations on this matrix. And that makes it a lot nicer. You don't have to know that, that was just something cool. Maybe I might put a problem like this on the bonus or something. Because I mean, we're at the end of the course, there's no real next topic to ask you a bonus about. So I'll probably just put a mixture of some random things like this or test you on stuff that we did way back in test 1 and 2. See if you remember that stuff. Yeah, remember how to compute a surface area? Boom! Surface area! Wasn't expecting it. Yeah. So I might do that. But yeah, so yeah, overall, final, nothing really to worry about. That's kind of it. We're not going to have a review session unless it's, by popular demand, it'll be after classes end, so I don't know. Your last test is on Tuesday. And that's purely on matrices, except perhaps for the bonus. And we'll kind of stop there. So we'll end early because I don't really have anything else to say. Do you guys have any questions about that?
No.
So I'll give you your test back. And it's good that we end early because I can go prepare for the talk that's in my other class, which you guys missed out. Anna was the only one who responded to my email.
I showed genuine interest.
I opened it. I opened it.
What up?
You guys missed out because I can't even record it.
Oh, I was just
He's talking about some high-level stuff. His bosses were like, you probably shouldn't publicize this. It's going to be cool. We're going to have a pizza party. You're going to chill. It's going to be fun. You guys missed out.
That is today.
That is today. So we'll stop there. I'll see you guys on Tuesday for the last test. Give you this back, and then we are done. Remember how to practice? I told you.
Beautiful
So
pen. Beautiful pencil.
Oh, yeah.